Welcome back to My Smart Learning. This is a lesson about weight and mass. It's predominantly for my Year 7s who are missing their lessons this week, their forces lessons. But this will be appropriate for GCSE students too, because we're looking at the difference between weight and mass. The learning objective then, are weight and mass the same thing? So by the end of this lesson, you should understand that they're not actually the same thing. We measure them quite differently. To start off then, with all my classes, I've been doing a recall quiz, a quick high five, a virtual high five, if you get them all right. Quick recall questions then. Number one, have a go at this, write these down and pause it after each question. At the end of it, I'll go through the answers, and if you get them all correct, you'll get a virtual high five. So, number one, in our recall quiz, PT, number one, what can forces do? So this isn't a one-word answer. There's a list of things forces can do, is what we did in our previous lessons back at school. What can forces do? Write them down, pause the video, write them down, and then we'll go on to question two. So question two, what is the unit of force? So that is just a one-word answer. What is the unit of force? Write that down. Question three, the force that pulls things down to earth. So the force that pulls things down to earth, what's that called? Question four, when two forces rub together, what is the name of that force? When two forces rub together, what is the name of that force? And question five, the force that will make a boat float. There you go, a bit of poetry there. What is the force that makes a boat float? If you press pause, just check your answers, and we'll get back to that. So the answers to question one, what can forces do? This wasn't a one-word answer. There's the obvious one where you learn at primary school. Forces can either push or pull, but there's some other things they can do as well. So if you get a push and pull at the same time, you'd get a twisting force or a turning force. Now the scientific word for that, a turning force, is known as a moment, but we'll come back to that later. What else can they do? They can, if an object is still, and if the forces are acting on it, the force can cause the object to start moving. So they can start an object moving, or the opposite, if an object's already moving, if you've got a force in the opposing direction, you can slow it down. So force can also start an object moving, speeding it up, and they can also slow it down. And there's one thing that also an object can do, is if a force is acting on an object, let's say a ball is coming towards me, and I head it, I can change the direction of that force, change the direction of the object. So if the ball's coming towards me, the object's flying this direction, I can head it towards you. So it's change the direction of the object. So they can push, pull, twist. They can start an object moving, stop an object or slow it down, speed it up as well, and they can change the direction of the object. So number two, what is the unit of force? The unit of force is newtons, named after Isaac Newton. Forces that pull things down, the force that pulls things down to earth is gravity, and that's what we're going to be focusing on today. And number four, forces, when two things rub together, that force is friction and causes a heating effect. And forces that makes a boat float is upthrust. All right, so if you got all five of those correct, then you get a virtual high five. Now, let's move on to this then. So, here is a Mars bar. There are other confectionery available. Can you guess the weight of the chocolate bar? And remember to use the correct units. So have a guess, how much do you think a chocolate bar weighs? Now, I'd probably guess a lot of people would look at the chocolate bar and say, oh look, it's about 250 grams. So 250 grams, how much will that weigh? Well, it would actually weigh 0.25 newtons. 0.25 newtons. Well, why? Why is it 0.25 newtons? Why isn't it 250 grams? Well, it's to do with this. Mass is the measure of how much matter or how many particles there are in an object. So the mass is always measured in grams. If I asked you for the mass of the chocolate bar, that could be 25 grams or 100 grams, depending on the size of the chocolate bar. But if I ask you for the weight, weight is something different. Weight is a force, and it's the measure of how much gravity pulls down on that matter. So weight is always measured in newtons, but mass is measured in grams. So you have to always get that correct. So mass and weight are not exactly the same thing. And it's this everyday language. If somebody asks me, how much do I weigh? Most people give their answer in kilograms or stones. But actually that's incorrect. Scientifically that's incorrect, because weight will be measured in newtons. So if my mass was 80 kilograms, you wouldn't say to someone, if someone says, how much do you weigh? You might say 80 kilograms, but the weight would actually be 800 newtons. But we don't go around saying I weigh 800 newtons. We tend to say I weigh 80 kilograms. But that's not your weight, that is your mass. So mass is the amount of matter, the number of particles, the number of atoms that make something, whereas your weight is how much gravity pulls you down on that particular mass. So if you were to travel to the moon, where the gravity is weaker, what would change? Now think about it, what would change? So you've seen the pictures on the moon where people are walking around the moon, and they're doing the moonwalk, not the Michael Jackson moonwalk, not, shuffling back and forth, not that kind of moonwalk. The moonwalk where you see the astronauts walking on the moon, they sort of look like they're floating. Why? We could jump higher because the gravity is 6 times less, because the moon's size is 6 times less than the Earth. So your mass will be the same. So if you're, let's say, 80 kilograms of mass, your mass will be the same, but your weight will be 6 times less. So for instance, if your mass is 60 kilograms, which is probably the average for a year 7, 8, 9 student, or probably about year 7 or 8, 60 kilograms of mass, your weight would actually be 600 newtons. So that would be on Earth. So on Earth, your mass would be 60 kilograms, but your weight on Earth would be 600 newtons. However, if you go to the moon, your mass would be the same. Your mass would be still 60 kilograms, but you'd weigh 6 times less. Your weight would be 100 newtons, because that's 6 times less. So you'd be 100 newtons. So you'd weigh a lot less. So you'd be able to jump a lot further. And that's why when you see the astronauts walking around on the moon, you can see them jumping really far. If you throw a ball, you should be able to throw it 6 times further, because your weight is less, but your mass is the same. So if you imagine I got a tin of beans and there was 1,000 beans in that tin on Earth, and I got into a space shuttle, there's still 1,000 beans in there. If I take it to the moon, there's still 1,000 beans in there, but the tin of beans would weigh a lot less. But let's say I carried on my journey into space and I flew to Jupiter. Now, if I wasn't hungry and I didn't eat the beans and there's still the tin of beans there, well, how many beans would there still be in there? There should still be 1,000 beans in that tin. However, what would happen to its weight? There'll still be 1,000 beans, and let's say it's 1 kilogram. On Earth it's still 1 kilogram. It'd actually be 10 newtons of weight on Earth. But if I take it to the moon, it'd still be 1 kilogram mass of beans, but it would be 6 times less of 10 newtons. But if I take it to Jupiter, it'd actually have the same mass. It'd have the same 1,000 beans in there, long as I don't eat it. But the weight will be much, much more. So it would be really heavy to hold a can of beans on Jupiter, because its weight would be a lot more, because that's to do with gravity. Gravity is how much it's pulling you down. And on Jupiter, the gravity is much, much, much more. It's a lot stronger, so it pulls things down with a lot more force. So here's a bit of a strange question. If I had 2 bags, and both bags had... one bag had feathers, had a ton of feathers, and another bag had a ton of bricks, which one would be heavier? So I've got 1 ton of feathers in one bag and 1 ton of bricks in the other bag. Which one would be heavier? Well, it's a bit of a trick question, don't you think? Because both of them, which is heavier, a ton of bricks or a ton of feathers? Well, they've both got a ton. So feathers, you automatically see, well, the feathers are going to be much lighter because they're feathers, and bricks are really, really heavy. However, if you've got the same mass of stuff, if you've got a ton of feathers and a ton of bricks, well, they're both a ton, they both weigh the same amount. But obviously the bag of the bricks will probably be a lot smaller because it's a lot more dense, it's all packed closer together and a lot heavier, whereas the bag of feathers will be huge because they're a lot lighter, each feather is a lot lighter. So it's a bit of a trick question. So what is gravity then? Gravity is this strange concept. It's a force that only can pull, it doesn't push. So it's a pulling force, and every object in the universe, anything that's got mass, has a gravitational pull. So right now, I'm trying to go flying into the camera because the camera is trying to pull me and I'm trying to pull the camera. But why isn't the camera flying into me? Why am I not going flying into the camera? I've got mass, the camera's got mass. The reason being is that we are tiny compared to the grand scheme of things, the bigger things. The bigger an object gets, the more gravitational pull it has. And hence why the moon is huge, it pulls you down. But the Earth is 6 times bigger than the moon, it pulls you down even harder. So right now the Earth is pulling me, but I'm trying to pull the Earth at the same time, but we have this pulling effect, the Earth pulls me down. Hence why you got that phrase, what goes up must come down. So if I throw a ball into the air, the ball will come back down. It's like when you have bonfire night and you got all those rockets going up into the sky, the next morning when you go out into the streets, you see all those rockets, those disparate rockets on the floor, because what goes up must come down. The gravity is going to pull it down. Only if you're in a space shuttle or a rocket where you can actually get out of the Earth's gravitational field strength, the gravitational pull, you need to hit something called the escape velocity, where you go fast enough with enough force to get out of the atmosphere, and then you can just carry on into space. But gravity is always a pulling force. It will always pull down. And the bigger the planet, the bigger the object, the greater the gravitational pull. So here's some arrows on this Earth. Which arrow is pointing in the wrong direction? So have a quick look at those arrows. One of those is in the wrong direction. Well, which one is it? And if you look at it carefully, you should have noticed that it's that one, because the rest of them are pointing towards the Earth. Gravity points towards the center of the Earth. So the center of any object, gravity always tries to pull towards the center of Earth. This one is obviously pointing in the opposite direction. So, who discovered gravity? Well, Isaac Newton didn't actually discover gravity. Gravity was always there. But what he did is he started to explain this notion of gravity and what it does and the importance of it. And when we go into the GCSEs, you'll learn more about Isaac Newton and about his 3 laws of motion. But legend has it that he was sitting under a tree contemplating, why do the planets stay in orbit? Why does the Earth carry on around the sun? Why does it keep in orbit around the sun? Why does the moon stay in orbit around the Earth? Why does the moon come crashing into Earth? Why don't we go crashing into the sun? And as he was thinking about that, trying to overcome his problem, legend has it, an apple fell from a tree, landed on his head, bump on his head, and that sort of eureka moment, he sort of realized that gravity was fundamental to how the universe was held together and how the solar systems stayed together. So that was Englishman Isaac Newton, very, very famous English scientist. He's so renowned and respected in the history of science that he's actually been buried in, I think it's in London, in the Westminster Abbey, where literally royalty will be buried. And he's had a place there showing you how much high esteem he has in the British history. Now, so Isaac Newton, the apple, the story goes that he's sitting under an apple tree and an apple fell on his head. He went on to explore why it fell down and came up with the theory and the mathematical equation, and he named it gravity. What do we use to measure gravity? We use a Newton meter, so we name it after him, Newton meter. You can call it a force meter or a Newton meter, and it's just a spring that stretches, and you have a little needle in there, and it will measure like 1 Newton, 2 Newtons, 3 Newtons, and so on and so on. So your weight is a measure of your newtons, but mass is measured in grams and kilograms. Okay, so a kilogram of apples would actually weigh 10 newtons. So a practical that you might do in school to measure either you do it for Hooke's law or when we're trying to work out elastic potential energy, and when we're looking at the forces. If I get a 100 gram mass and I put it on my Newton meter, you should get 1 Newton. And then for 200 grams, you should get 2 Newtons. And you should notice the pattern. It should be, what is the pattern? Directly proportional. As you increase the mass by the same amount, the force should increase by the same amount. So 100 should be 1 Newton, 200 grams, 2 Newtons, and so on. 300 grams, 3 Newtons, 500 grams, 5 Newtons, 600 grams, 6 Newtons, 700 grams, 7 Newtons. 1,000 grams then, it's just 1,000 grams or 1 kilogram. It's like a normal bag of sugar, normal size bag of sugar, is actually 10 Newtons. 10 Newtons. So 100 grams is 1 Newton and so on. So the equation then, now this is a GCSE equation that you need to memorize your formulae, but we'll start to like you guys to do it in year 7 as well, so you're ahead of the game. Your weight then, how do we calculate it? It's your mass in kilograms times by the gravitational field strength. We just call it gravity here just to keep it simple. When you get to GCSE, you'll need to call that gravitational field strength. And different planets have different gravitational field strength. On Earth, the gravitational field strength is 10. That's rounded up. If you want to be more accurate, we'd call it 9.81. But just to keep it rounded to simple numbers, we'll call it 10. And it's a constant, it stays the same. Earth's gravitational field strength is 10 newtons per kilogram. So if my mass is 100 kilograms and my gravitational field strength on Earth is 10, then my weight would be 100 times 10, which will give me 1,000 newtons. So that would be the weight, 1,000 newtons. Remember, your weight must be in newtons. So gravity on Earth causes the man to accelerate towards it. Its effect is the same everywhere. So no matter what country you go to, the gravity will pull you down by the same amount on Earth. So gravity on Earth is said to be 10. So we use this number 10 newtons per kilogram. But in your exam, when you do GCSE exam, they might give you a number that's more accurate. So it might give you 9.8 or 9.81. So whichever number they give you, you use that number. If they don't give you a number in the exam, you have to assume rounded to 10. Okay, so this is what the equation looks like. So your weight is your mass times your gravity. Now if you haven't come across one of these little formula triangles before, we can use it depending on the question might ask you to calculate the weight. So you'd cover up the weight, and what you're left with is mass times the gravity. So you multiply those two numbers. If it's asking you, if the question's in grams, if the information gives you in grams, you need to convert that into kilograms. So for instance, if it's 500 grams, you'd have to divide it by 1,000, so 500 grams would be 0.5 kilograms, and then you multiply it by the gravitational field strength. But if I was trying to work out the mass, I'd cover up mass, and the two numbers I've still got left is your weight and your gravity, and you divide it. So if it's over the top, you divide it. So it'd be weight divided by the gravity would give you the mass. If I wanted to work out the gravity of the particular planet, I'd have to cover that up, and then it would be the weight divided by the mass, and that would give you the gravity. So the astronaut has a mass. Here's some questions for you to have a go at. So can you work these answers out based on what we've said? The astronaut has a mass of 80 kilograms. But when will he weigh more? Will he weigh more on the moon, or will he weigh more on the Earth? So how would we calculate that? Well, we need to know the gravitational field strength on the moon, and we'll need to know the gravitational field strength on the Earth to calculate his weight. So if we assume gravity on Earth is 10, and if we give you the gravity on the moon is 1.5, it's actually, realistically, it's actually around a little bit more than that, it's about 1.6. But if we just give the number 1.5, which is a more simpler number to use, where would he weigh more? So how would you weigh or calculate the weight of the man on the moon and the Earth? If you pause the video, get your calculators out and have a go at those questions and see if you get those right. Now if you've had a go at that, to work out the weight, remember we covered up the weight, it's mass times the gravity, so it's 80 times 1.5. So that will give us 80 times 1.5, which gives us 120 newtons, whereas the weight on Earth will be 80 times 10, which gives you 800 newtons. So the man weighs 800 newtons on the Earth, so he weighs more on Earth than he does on the moon. So to finish off then, here's a table, and if you pause, draw out the table and see if you can calculate those missing numbers, and that's the kind of what you'll be able to do it for your GCSE exam. So for instance, the mass of the pack of crisps is 125 grams. You must make sure you convert it into kilograms. So to convert it into kilograms, grams into kilograms, you need to divide it by 1,000. So if you divide that by 1,000, if I put a dot at the end, I go back 3 spaces, 1, 2, 3, that actually weighs 0.125 kilograms. So that's your mass, 0.125 kilograms. I then have to times it by 10, which will be my gravity on Earth. So if it was 0.125, times it by 10, it will now 1.25 newtons. So my pack of crisps weighs 1.25 newtons. Am I right? Well, remember in my previous slide I showed you that 100 grams is about 1 newtons. So look, 100 grams, yeah, 1.25 newtons. So that's right. So have a go at filling those in. If you press pause, and I'll go through the answers very quickly now. So if I was trying to work out the mass going backwards, I'd have to actually times that by 1,000 to work out what it is in grams. But do I actually want a car in grams? Probably not, because I'll get a huge number. I'll get 1,500 with 3 zeros after it. But if I wanted to work out the weight, it would be 1,500 times 10. So all I need to do is add another 0 at the end of that. So it will be 15,000 newtons. 10 bags of sugar. So 10 bags of sugar, I need to divide that by 1,000. So that will be 10 kilograms. So 10 kilograms for my bag of sugar. 10 times 10, because it's my mass times my gravity, 100 newtons. So 10 bags of sugar would weigh 100 newtons. My ball weighs 400 grams in mass, but my weight would be, so my mass in kilograms will be 0.4, because I have to divide it by 1,000, make the dot go back 4 spaces, 1, 2, 3. 0.4 kilograms, times that by 10, so my ball weighs 4 newtons. And the last one you have to work backwards. Well, if I've got 250 newtons, if I'm timesing it by 10, the opposite of timesing it by 10 is divided by 10. So if I divide that by 10, I'd actually get 25 newtons. So 25 kilograms. So the mass of this mobile phone would actually be huge. That would be one massive mobile phone. So if I want to convert that into, I'll have to times it by 1,000 to go all the way back. Okay, so that'll be like a huge phone. Now, I hope that's been helpful. If it's been useful for you and you've learned something today, please like and then subscribe and share it with your friends, so then more people can do a bit of learning while we're off school at the moment. I hope you're keeping well, keep healthy and stay safe, and I'll see you on the next video. Take care.